Hey guys, we are on our final chapter of Chem 2B, and that is chapter 20, Organic Chemistry. So this chapter is just an introduction to organic chemistry. For those of you that will be continuing on to take OChem, it's a full year course, so this is not even scratching the surface, it's just maybe touching the surface, but it'll give you a little bit of a backbone so you're a little bit more prepared for it. So there's only 4 sections, and they are on hydrocarbons, alcohols and ethers, aldehydes, ketones, carboxylic acids and esters, and amines and amides. There are way more than this, just these groups of organic molecules, like I said. So, again, this is just barely starting. So organic compounds all contain carbon that is bonded to hydrogen in some part of the molecule. Um, a bunch of them are formed by living things. Some are also formed by geological and artificial processes. We hear the term carbon-based life forms, where my Star Trek fans at. Um, Carbon-based things are all around us. Organic chemistry literally centers around the element of carbon. Inorganic chemistry looks at everything else, so it's kind of crazy. So we're going to start with 20.1 hydrocarbons, where we will explain the importance of hydrocarbons and the reason for their diversity, name saturated and unsaturated hydrocarbons and molecules derived from them, and describe the reaction characteristic of saturated and unsaturated hydrocarbons, and finally identify structural and geometric isomers of hydrocarbons. So again, organic compounds contain carbon bonded to hydrogen and other carbons in them. So there are such thing as inorganic carbon compounds. Something like a carbonate, cyanides, and simple oxides are not considered organics because there's no carbon-hydrogen bond in them. But these organic compounds are used in many different things like plastics, pharmaceuticals, soaps, they're all over. And all living things on Earth are formed mostly of carbon compounds. And like I said, we're carbon-based life forms. So we're going to start with the basic type of organic compound it's also a hydrocarbon, and these are called alkanes. Um, these are called saturated hydrocarbons, which means that each carbon has um, has all single bonds, and it also has the right number of like carbon to hydrogen bonds. But it's all single bonds, really, is what it comes down to between all the carbons when they're bonded together. So these alkanes contain only single covalent bonds between carbon atoms. And each carbon that's in the molecule has sp3 hybrid orbitals, and it's bonded to 4 other atoms. You could have 1 carbon bonded to 4 hydrogens. You could have 2 carbons bonded to each other, and then each of them has 3 hydrogens. But every carbon has 4 bonds. No more, no less. Now, hybridization that occurs makes it so that chains of carbons end up having a zigzag shape because there's a 109.5-degree bond angle. Lewis structures are often used to depict them, so you might see something like this, but it doesn't show you really any bends or anything. You don't have these 90-degree angles, so that's something to keep in mind. So in reality, this compound would look more like this. Well, so again, not 90-degree angles. We're talking 109 degrees, but it's kind of hard to draw that. There are different ways of drawing organic compounds. There's always the Lewis structure. We have what are called condensed structural formulas, also called condensed formulas. And we also have skeletal structures or line angle. I tend to say line angle, but I'll use them interchangeably. So the condensed formula basically shows bonding in a molecule. So you might see something like this: CH3, CH2, CH2, CH3. So this is showing you that you have a carbon with 3 hydrogens that's bonded to a carbon with 2, to a carbon with 2, to a carbon with 3 hydrogens. And it's just to save room. Sometimes they might also be written, with a line in between. Again, it's just to save room though. And then the skeletal formula omits the hydrogens and it uses bends and the end of a line. So anytime you have an end of a line or a bend in a line, that represents a carbon. So for instance, this molecule here that I've done the condensed formula for, we have 4 carbons. So we would go 1, so here's 1 carbon, 2, 3, 4. So there's 1, 2, 3, 4 carbons. So literally that zigzag represents this same molecule. So when you see something like this, you see, okay, I see this end here. So that's a carbon. So what I used to do when I was first learning these, I would write in a carbon and I'd go, okay, this carbon, 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 and then I'd look at like this end one and say, okay, this carbon has 1 bond to another carbon, which means it needs 3 hydrogen to fill up its bonds. This next one needs 2 hydrogen. And so this is what I would do before I was comfortable being able to say, okay, just look at a structure and say this carbon has 3 hydrogens. So that's something you can do if it helps you to visualize these types of structures. So this is showing you Lewis structure for a couple different hydrocarbons for some alkanes, as well as the ball and stick models and space filling models for them. And then you can see their names. We're going to talk about how to name them in a minute. And then you can see also their condensed structural formulas. So I just kind of want to point out methane is CH4. So meth meaning 1. So that means there's 1 carbon. And ane, A-N-E, means it's an alkane, meaning single bonds. Ethane, eth means 2. And then the ane tells us that they're singly bonded to each other. Pentane, pent meaning 5, the ane telling us all single bonds. Now, one of the reasons you don't often see these condensed formulas like C2H6 or C5H12 for pentane and for ethane is because those don't tell you anything about the structure. For something like ethane, you can pretty much tell that the 2 carbons are going to be bonded together because you can't have a hydrogen with more than 1 bond. But for pentane, C5H12, there could be a bunch of different ways you draw the structure. And we'll talk about branching and stuff later, but that doesn't give us any structural information, which is why we like doing condensed formulas when we're maybe typing it in a line. So this is giving you another example looking at 3 different ways of looking at a structure. And you can see some branching going on. So here we have this expanded formula or expanded structure. So you can see all 4 bonds for every single carbon. And then the condensed formula definitely brings down that space. And you can see, okay, so that there's like a branch here and a branch there. And you can see where the hydrogens are with each carbon. And then the skeletal structure, which again saves more space and looks really cool. I always thought skeletal structures look really awesome. A lot of times you see them drawn poorly and inaccurately when people try to draw science. But you might also see them if you look at like a pharmaceutical insert, because they'll draw the structure of your active ingredient in whatever medicine you're looking at. And they're practically all organic compounds. So skeletal structures you will see quite a bit. So here's a couple examples where we want to draw the skeletal structures for these 2 molecules. So one thing that I would do when I was first learning this is when I'd be given something like this condensed structure, I would go, okay, I'm going to play connect the dots where each C is a dot and just kind of draw lines. And then that would tell me, okay, now I know basically the outline for my skeletal structure. So there's A. We're not too terribly worried about bond angles, and I'll talk more about that later. So yeah, and then B, we go, okay, I have 1, 2, 3, 4, 5, 6, 7 carbons. So we're going to do a zigzag because this is just a nice straight chain. So when I draw my first line, that's 2 carbons, 1 on the end, and then at this first bend. So that's 1, 2. Now I just added a third, 4, 5, 6, and 7. And then you can go back and check. 1, 2, 3, 4, 5, 6, 7. And here's another couple example for some skeletal structures. This first one, we have a cyclic alkane. So you see this ring where the carbons are connected in a ring. And then it's got a little guy coming off the side. So we're going to draw a hexagon, which in organic chemistry, you get pretty good at drawing hexagons. There's actually hexagonal graph paper, fun fact. For those of you that maybe play Dungeons and Dragons or do other type of tabletop RPG, you may have seen it before. You can also get like giant hexagonal like wet erase marker boards for doing like positioning with your with figurines for D&D. I am speaking from experience here. I also personally have some notebook hexagonal graph paper, which is very nice for drawing organic structures and making them look pretty. All right, and then for B, we have 1, 2, 3, 4, 5. So there's 1, 2, 3, 4, 5. You could also draw for B, for instance, 1, 2, 3, 4, 5. It doesn't matter. 1, 2, 3, 4, 5. All of these are the exact same structure. We're all showing 5 carbons in a row connected to each other. So this one wants us to figure out the chemical formula of this molecule. So what I do is I go in and I look at every corner and end and put in a carbon. So I go, okay, there's all my carbons. And now let's go in and fill in the hydrogens that they need to fill in their bonds. So let's start on these end carbons. This one here is a CH3 since it has 1 bond, so it needs 3 more. This other one is going to be a CH3. This carbon here is going to be just 1 hydrogen because it already has 3 carbon bonds. Same with this other carbon that it's attached to. And then all the rest of the carbons in this ring are going to each need 2 hydrogens to fill in their 4 bonds. So if we wanted to do just the overall molecular formula, we have 8 carbons, and we total up all our hydrogens and see there are 16 of them. Here's another example that wants a chemical formula. So let's go in and fill in our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops. 9 carbons. So we know we have a C9. Now we'll start filling in our hydrogens. Actually, I'm going to kind of draw these condensed. One thing you might see with a condensed formula is if you have a carbon that's like on the left side, instead of, you might actually see it written like H3C. It means the same thing. Some people just do that just to kind of insinuate that it's the carbon that's bonded, not the hydrogens. It means the same thing. So we're going to fill in our hydrogens. Now notice these 2 carbons here already have 4 bonds, so they do not have a hydrogen on them. They are just carbon. And then this carbon here is a CH2. Again, you can draw that H2 below just to show that it's the carbon that's bonding. So the total of our hydrogens, we have 3, 6, 9, 12, 15, 18, 19, 20. So this is C9, H20. So non-cyclic, so that means there's no rings in the structure, alkanes, have a chemical formula of CnH2n plus 2. So let's say we have an alkane that does not have a ring and it has 5 carbons. And we want to say how many hydrogens it has. It would be 2 times 5 plus 2. So that means it would be H12. If I told you you had 8 hydrogens, and we want to know how many carbons. So we know that 8 is equal to 2n plus 2. So then n is equal to 3. So we have C3H8. The number of carbons in an alkane has no limit. You can have just a ton of carbons in a chain. In fact, in things like biochemistry, you have just an insane number of carbons. Waxes and fats can have like 20, 30 carbons in them. Now, one thing we should know is that the more atoms that are in a molecule, the more intermolecular dispersion forces that are happening. So, because you have more atoms, you have more interaction between the electrons and other molecules. So this is going to then raise their melting point and boiling point because they're interacting with each other more. And then when you have hydrocarbons that maybe have the same formula, they can have different structures. So when I was talking earlier about the pentane formula at C5H12, we can have what are called structural isomers or constitutional isomers, where they have the same molecular formula, but different spatial arrangements of the atoms in their molecules. So they can be branched or have unbranched chains. And we'll look at some examples in a moment. But you do have to be careful because sometimes a Lewis structure may look different, but actually represent the same isomers. And I have these little GIFs here to represent what happens. So at these carbon-carbon single bonds, they rotate. So you can see this carbon here rotating. And same over this other structure over here. This is N-butane. So you can see there's 1, 2, 3, 4 carbons. And you see as it's rotating, the shape of it looks like it's changing. So if I might draw this like that, but in reality, it can rotate and it might do that for a moment. Okay, still the same structure. This is still butane. You still have 4 carbons in a row, each of them with the same number of hydrogens. It's just because it's rotating. So it's worth it to kind of highlight the continuous chains of carbon and looking at where branches come off. And we'll talk about naming, which also really helps with identifying if they're isomers or not. So this is kind of showing you some properties of some alkanes with their molecular formulas, and then you can see as we add more carbons and more hydrogens, our melting points get higher and higher. Same with our boiling points. And then you can also see the number of isomers, how many that increases by. It's almost exponential. So these are 2 structural isomers, N-butane and 2-methylpropane. So these are both C4H10. And butane is just the straight chain, but we could also have this 2-methylpropane where instead your carbon in the center has a little branch coming off of it. This is still 4 carbons and 10 hydrogens. So this is why just writing like a condensed formula doesn't always work, especially once you get to like 4 or more carbons in a structure, because you can start having branches. Now, all 3 of these structures that are shown here are all N-butane. They're not isomers of each other because they actually have the same arrangement of atoms and bonds. You have 4 carbons in a row in a straight chain or continuous chain, maybe is a better way to say that, each with the same number of hydrogen. It's the same molecule. So let's talk a little bit about naming alkanes. Being able to properly name alkanes is kind of the backbone of organic chemistry in general, because a lot of names for organic molecules are based on the alkane base name. So there's a few different methods of naming, but the biggest method is system is using the International Union of Pure and Applied Chemistry, or IUPAC, and this is called nomenclature, so naming. So we have some basic rules for naming alkanes. The first thing you want to do is identify the longest continuous chain of carbons. So it just keeps going like in a straight line, if you will. And that tells you how many carbons are on your base chain or your root name. And all alkanes that have a name that ends in the prefix of ane, because the ane means that they're all single bonds between the carbons. And then we use a prefix to go with it to identify how many carbons are in the longest chain. And these are the basic prefixes for 1 through 10, meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. So maybe you have a methane, which has 1 carbon, or ethane has 2 carbons, propane has 3, nonane has 9, decane 10. Then the next thing you do is look for any branches or substituents that are coming off, that might be coming off of your chain. And branches are what are also called functional groups, which these functional groups influence a lot of the chemistry of our molecule. We'll talk more about those later. And these replace the hydrogen atoms that are on a carbon chain. And we use prefixes to identify what that branch is. And if you have multiple branches, we name them individually and put them in alphabetical order in front of our root name of our molecule. We have to number the carbons in the chain, and there is some numbering rules that we'll talk about. And we use that carbon number to identify the branch that's coming off of it. One example of substituents are alkyl groups, and this is when you have like a methyl group, methyl meaning 1 carbon with 3 hydrogens. It's not part of the main chain, but it is a carbon branch. You can have halogens, so we might say bromo, chloro, fluoro. Those are like the main substituents we talk about with alkanes. And you can have more than one. You can have dibromo, dimethyl, diethyl, trifluoro. Those all exist also. So these are some examples. So propane, if we just said propane, we mean a straight chain alkane with 3 carbons in a row, all single bonded. Now, if I said 2-chloropropane, the first thing that I always do is I look for my root name. I see propane, so I go, okay, I have propane, so I'm going to draw propane, 3 carbons. 2-chloro, so that tells me carbon 2 has a chlorine coming off of it. With something like propane, carbon number 1 is always on the end of a chain. So I'd go, okay, carbon number 1, I'm going to say it's this one, and then this one has to be 2, this one has to be 3. We could also instead, you don't have to number from left to right. We could say this is carbon 1, this is carbon 2, this is carbon 3. And that all is going to depend on how the structure is drawn. And then we have 2-methylpropane. And also notice we say 2 to represent the carbon, and we'll put a little dash there. So it's 2 dash and then whatever your branch is. So 2-methylpropane, okay, that means it's the center carbon, is going to have a methyl group. We could also have 1-chloropropane. So now that means that the chloro is on carbon 1. So I'm going to say carbon 1 is this guy here. So I'm going to then draw this and put a Cl. So now this is a carbon with 2 hydrogens. So if I can also draw this like this, CH3, CH2, CH2, Cl. It means the same thing. Or we could have also put it on the other side. So we could have done it like this. It means the same thing. The next one, we see 2,4-difluorohexane. So we see hexane telling us we have 6 carbons that are in our continuous chain, okay, in our straight chain, if you will. And then we have a fluoro, so a fluorine on carbons 2 and carbons 4. So we go 1, 2, 3, 4, 5, 6. And they chose to start their numbering on the right side. So this was carbon 1, which means carbon 2 is here. Oops, not chloro, fluoro. Also notice that we want to do it so that we have the lowest possible number going with our carbons. And then this last one, we see 1-bromo, 3-chlorohexane. So again, hexane as our root, so we have 6 carbons. And then carbon 1 has a bromo. So that's a bromine. And carbon 3 has a chloro. So we have 1, 2, carbon 3 here has a chloro. And we put those branches in alphabetical order. Bromo comes before chloro. So here is an example. We want to name the molecule whose structure is shown here. So the first thing we want to do is find our longest continuous chain of carbons. And we see right here we have 4 carbons in a row. There's our chain. So we have 4 carbons, meaning our prefix is bute. They're all single bonds, so this is butane. And then we notice that 2 carbons have branches coming off of them. This one on the end has a chloro. This one here has a bromo. So we also know we have a bromo. So it has to come first. It's alphabetical, dash some number, and then chloro. So now we have to decide how to number our carbons. If we wanted to make carbon number 1 on the end, that would mean then this is 2, 3, and 4. That would mean we'd have 3 bromo, 4 chloro. Those are kind of big numbers compared to our structure. But if we did carbon 1 on the right, and then this is 2, 3, 4, then that means we have 2 bromo, 1 chloro. Those are our smaller number combinations, so that's what we're going to go with. 2 bromo dash 1 dash chlorobutane. Here's another example. So we've got 1, 2, 3, 4, 5 carbons in our longest chain, which means we have a pentane, pent meaning 5, ane to tell us we have all regular carbon-carbon single bonds. And then we notice we have 2 bromines, and they don't have to be coming off the same carbon to do something like dibromo, but in this case they are. And then we have an iodine, which is called an iodo. So we know we have a dibromo, as then some type of number iodopentane. So this one, if we start by numbering on the right, we would go carbon 1, this is carbon 2, 3, 4, 5. That's going to be our lowest numbers. So we notice carbon 3 has 2 bromos on it. So we have to do this, we'd say 3, comma, 3 dash dibromo. So this is saying carbon 3 and then carbon 3 again has a bromine. Because you could have maybe 3, 4 dibromo or something. So it's also important that even if it's on the same carbon, that you specify 3, 3 dibromo, and then carbon 2 has the iodo. Iodo is just fun to say. So these are some examples of when you have a substituent or a branch that is an alkyl group. So the way that how we call them is we take, the alkane name and we get rid of the ANE and replace it with YL. So if we have an extra CH3 branch, it's a methyl. If it's an extra C2H5, it's an ethyl group. You can't just have an ethyl group floating around. So it has to be coming off of a chain. So here's an example. Here's propane, and then instead we take one of these hydrogen and replace it with a CH3. And now we have 2-methylpropane. So now I was talking about how we look for the longest carbon chain, continuous carbon chain. We can't go, okay, this goes 1, 2, 3, 4 carbons, because they're not actually in a row. We want carbons all connected to each other. So we could either say this carbon chain here, we have 3 carbons, or we could go this way, there's still 3 carbons, or we could go this way, still 3 carbons. I'm going to go this way because I'm a rebel. So we see no matter what that there's 3 carbons, so we have a propane. And in this case, it doesn't matter where carbon 1 is, since it's the center carbon that has a branch coming off of it. So if we look at the center carbon, we see we have the CH3 coming off of it. So this is a methyl group, and it's on carbon 2. So 2-methylpropane. Here's some more examples. We have this long chain that's 7, so that's a heptane. And you always, again, want to go with the longest chain. So we see, okay, that one's 7. What if instead I look and go, okay, I've got 1, 2, 3, 4, 5. No, 5 carbons is less than 7. What if I tried this way? 1, 2, 3, 4, 5, 6. Nope. 6 again is smaller than 7. Oh, 7. Sorry, that's 7. So you could also do that. That is still a continuous chain, so that is still a heptane. And then instead of the numbering you'd have, this would be carbon 1, 2, and then this is still, though, carbon 3, having an ethyl group coming off of it. So heptane, and then ethyl is our branch, and it's on carbon 3, 3-ethyl heptane. This guy here, 2,2,4-trimethylpentane. So we see 5 carbons is our longest chain. And then the best way to do our numbering is on carbon 2, we have each has 2 methyls, and then carbon 4 has a methyl. So this one might be a little confusing because if you were to make like this carbon 1, and then this would be 2, 3, 4, 5, for instance, it still ends up being 2,4,4-trimethyl. But that ends up not being the lowest overall combination of numbers. 2,2,4 is still overall lower, if that makes any sense. And then this last one here, 4-isopropyl heptane. So we have 7 carbons in a straight chain. And then we have this group here. This is called an isopropyl group. There is a table that I'll bring up in a slide or two, but your book also has one showing you some common alkyl groups. So this one is called an isopropyl, and it's on carbon number 4. So 1, 2, 3, 4. Carbon 4 has an isopropyl. So this is that table I was talking about. These are some names and formulas for some alkyl groups that you might find as branches from your carbon chain. And these, again, are replacing a hydrogen that would normally be on a carbon to fill its 4 bonds. So here's an example. We want to name the molecule where we're given a structure. And the book was nice enough to number the carbons for us. I, however, will not be, which we'll see in another example, but they already went ahead and told us that there are 6 carbons in this longest chain. They already even identified it for us and numbered the carbons. Isn't that nice? I'm not that nice. Anyway, so we have 6 carbons, meaning we have hex, and they're all single bonded, meaning it's hexane. And then we see that carbon 3 has a 2-carbon alkyl group coming off of it. 2 meaning F, and since it's an alkyl group, it's a branch, it's an ethyl. So this is 3-ethyl hexane. Let me write that prettier. There should not be a space between ethyl and hexane. I'm just bad at spacing my letters. All right. Here's another example. So our first step is to find our longest continuous carbon chain. I always like looking at branches, like where it looks like maybe you have a branch and being like suspect of it. Because, you know, a sneaky professor, cough, cough, may do something like that on an exam where you think that the straight chain is the longest, but it's actually not. So let's start down here and say, okay, maybe we go 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 carbons there. And let's take another color and say, okay, let's look at this straight chain up top. And we say, okay, 1, 2, 3, 4, 5, 6, 7, 8. Also. So that's also 8 carbons. So either of these chains, they're the same thing. So those are identical groups, if you will, coming off of that center carbon. So I'm going to go ahead and use my red chain because I like being a little different. So now we need to figure out our priority. Where is this alkyl group? What carbon number is it coming off of? If I start with saying this is carbon 1, then we would go 1, 2, 3, 4, 5. Carbon 5 would have the branch. But if I started at this bottom carbon, say let's try this as carbon 1, we'd have 1, 2, 3, 4. So that is going to be our carbon numbering because that's a lower number. So we have 8 carbons, so this is an oct, all single bonded, so it's octane. The group coming off of it has 3 carbons in a straight chain. It would normally be propane if it was an alkane. It's an alkyl, it's propyl. So this is propyl, and this is 4-propyl octane, since it's on carbon 4. So let's talk a little bit about alkane reactivity, and I don't know why I put alkane reactivity and just the alkane reactivity. So alkanes burn in the presence of oxygen, and these are redox reactions, aka combustion. So if you remember, like chapter 4 or 5, when we talked about reactions in Chem 2A, combustion reactions involve a hydrocarbon and oxygen reacting to produce carbon dioxide and water. So this is a combustion reaction. It's also redox. The carbon and the oxygen, well, no, never mind, not oxygen. Oh yeah, oxygen, because it goes from O2 with a 0 oxidation state to its -2 state. So carbon and oxygen undergo some redox. Some examples of where you may have seen these: methane is the main component of natural gas. So if you have a gas stove, methane tends to be the gas of choice for it. One thing I want to specify, though, is natural gas or methane gas does not have a smell. So if you leave your stove on and you smell something, it's actually a chemical that they add to it that has a smell to it. Usually it's either a sulfur compound or sometimes these are called thiols, where you have a sulfur in an organic molecule. So it's something that smells so you can see if your stove is on. Butane is used for lighters, so butane lighters and camping stoves. So you can get little butane mini cylinders. Like if you go camping and you have a little portable gas stove, it's usually butane. Gasoline for our cars tends to be a mixture of 5 to 9 different carbon alkanes and other additives. Kerosene, diesel oil, and fuel oils are mixtures of high molecular weight alkanes. And we use what's called fractional distillation to separate crude oil, which is what we get from the ground, from fossils, and that's separated then into various fuels. So this is a picture on the left, and then on the right is a schematic of fractional distillation of crude oil. So it goes into this heated column, and the lighter, more volatile organic compounds are going to come out through the top, and then it separates them based off of their density as they boil in the column. And then the residue is pulled off. So this is how we get our different types of fuels. Now, one type of reaction that alkanes can go through, and we are literally, for most of these types of compounds we're talking about, looking at one type of reaction. These go through a substitution reaction. This is not the only type of reaction. This is just the only type we're looking at. And what this means is you have a normal hydrocarbon, and one or more of those hydrogens is then replaced with a different atom or group of atoms in a chemical reaction. So it's not like if I gave you 2-methylpropane, that's a substitution reaction. No, I'm talking about like we did a reaction to get 2-methylpropane or something, which normally we're not going to do that. But so no carbon-carbon bonds are broken from your main chain. The hybridization of your carbon does not change. All the carbon stays sp3. An example is when you take ethane and react it with chlorine gas to form chloroethane and hydrochloric acid. And the carbon-chlorine portion is an example of what's called a functional group, which is a part or a moiety of a molecule that imparts a specific chemical reactivity. So this is that reaction. So if I give you an alkane and a halogen, this is basically the only type I might give. It might be any alkane, and you can predict the product for me. Maybe I'll tell you this is the hydrogen that gets replaced, or I'll let you be creative because sometimes it can be different hydrogens that come off. So this hydrogen comes off and is replaced with a chlorine. So you end up, when you do organic chemistry, you look at these things called mechanisms. But basically, chlorine grabs this hydrogen and takes off as HCl, and you have this other chlorine that comes in for the carbon. Now, one thing I want to specify here is with naming this compound. I've talked about how when you have branches, you number the carbons. One thing I didn't specify is you need to start numbering them when you're at 3 carbons or more. Because if, let's say we said 1-chloroethane, it doesn't matter which carbon here is number 1. There's only 2 carbons. So if I just say chloroethane, it doesn't matter which carbon it's on. Now, if I said dichloroethane, then we might have an issue. So if I said to draw dichloroethane, so I see ethane, so I could have carbon-carbon, and I have 2 chloros. So do I put 2 on one carbon, and then the other one stays as CH3? Or do I do 1 chlorine on each carbon? So in this case, you do have to specify some numbers. So if I just told you dichloroethane and then name it, for instance, let's say I wanted this one, you drew this. Well, you have 2 chlorines on the same carbon. So this would be 1,1-dichloroethane. Or if I had, where each carbon has a chlorine on it, and notice it doesn't matter which hydrogen I replace with the chlorine. All those hydrogens coming off of the carbon of each carbon, they're identical to each other, so it doesn't matter. So this would be 1,2-dichloroethane. This one doesn't quite matter which one we say as is carbon 1 or carbon 2, but we do still have to specify 1,2 to say that there's a chlorine on each one. So I just wanted to specify that with you guys. If you just had ethane and there's just 1 chlorine we're putting on it, like here, it's just chloroethane. You don't have to say 1 chloro. That's going to be implied. Now, our next type of hydrocarbon is called an alkene. Sounds like not alkane, it's an alkene. Ene meaning double bond. So an alkene is an organic hydrocarbon that has 1 or more double bond. So we call these unsaturated. So that means that each carbon, or that there's at least 1 carbon that has a double bond. It doesn't have the maximum number of hydrogen. So the carbon atoms that are in the double bond itself are linked by a double bond, whereas they have 1 sigma bond and 1 pi bond. And these carbons also have a trigonal planar sp2 geometry. One example of that is ethene, also known as ethylene. Starting at 4 carbons, the double bond can be on between 2 different carbons, can be between different carbons in the structure, and then you have to do numbering of your carbons to specify where it is, and we'll look at that. But first, I want to show you the structure of ethene. So eth meaning 2, ene meaning double bond, meaning there's a double bond. So those 2 carbons have to be double bonded to each other. There's nowhere else that we can have a double bond. And so then we go in, and after we do that double bond, we fill in the hydrogens so that each carbon has 2 bonds, or 4 bonds, I'm sorry. So the carbons each already have 2 bonds, and then they get 2 hydrogens, so each one now has 4 bonds total. This next one here is propene. Prop meaning 3, so we have 3 carbons bonded to each other. ene telling us there's a double bond. So we could either draw propene like they have with that double bond there, or we could do it on the other side. To do it the line angle mode, that's kind of that's what I just drew. You can still do that. You just draw 2 lines for the double bond. Or draw a second line, basically. Draw it like that, or you could draw it like that, however you want. We don't need to specify a carbon number for this double bond because no matter what, it's going to be between carbons 1 and 2. We can't have it on carbon 3 because we want the lowest number. But now we go over to this 4-carbon one, and we see 4 carbons in a row, so that would be a bute in a continuous chain. And we see a double bond, so this is going to end in ene to tell us there is a double bond somewhere. Now, where that double bond is, we have to number our carbons. And so this double bond, think of it as it's a functional group. It tells us, okay, this is an alkene. It goes through, has different chemistries. So lowest possible number is that we have carbon 1, 2, and then these other 2 here are 3 and 4. So the double bond is between carbons 1 and 2. We don't say 1, 2, we just say 1. So we say 1 butene. So we say the double bond starts at carbon 1. Okay, now another isomer of this is we could have 2 butene. So if I tell you 2 butene, that means then that the double bond is on carbon 2. So that means it's not going to be on the end. It means it has to be on one of these second carbons. So I'm just going to put it there and then fill in my hydrogens. So in this case, we can say this is carbon 1, this is 2, 3, and 4. So it goes from carbon 2 to 3. We just say 2 butene, that's where our double bond starts at carbon 2. One example of some alkenes is some polymers. Polymers are plastics, basically. Not all of them are, but polymers are large molecules made up of repeating units. These units are called monomers. There can be natural ones like starch. And actually, I believe DNA is considered a polymer. Or synthetic like polyethylene, polyvinyl chloride, aka PVC, and polystyrene, which is what makes up styrofoam. There's a bunch of different properties and uses for polymers, different things you can do to them. These are some example of polymerization reactions, and this is making polyethylene, so poly meaning many ethylene meaning many ethanes. No, this isn't something you have to be able to do, but basically, yeah, the catalyst, and then you end up breaking these double bonds, turning them into single bonds, and all these carbons end up bonded together in this big straight chain. And then there are so many different polymers. These are some plastics. If you notice on your plastics, they usually have that little angle, the triangle with little arrows with a number in the middle. And that actually is there to tell you what type of polymer it is, which then is used for recycling codes. So this lets you identify it and then how to recycle it. So when it comes to naming alkanes, you've already kind of seen this. It's derived from the alkane name, except you replace the ane end of the name with ene to signify there's a double bond. And then you identify the carbon number, the lowest number that has the double bond. You can have more than one double bond. You might have a diene, so you might have 2, 3 octadiene, for instance. You can have branches and substituents also in your alkene. But that double bond comes first in priority. So that's where you're going to determine your carbon numbering. But I don't think we're worrying too much about that here. So this is the same things I was talking about earlier. Ethene, propene, we don't need to number the carbons because no matter what, they're going to be on carbon number 1. Then we have 1 butene versus 2 butene. showing us, okay, 1-butene has a double bond starting at carbon 1, 2 it starts on carbon 2. So 1-butene and 2-butene are called structural isomers, which means they have a different arrangement of atoms in molecules. Another important type of isomer, especially with alkenes, are called geometric isomer. And these occur when you have the same type of atoms attached to each other in the same order, but they have different geometries. And this occurs because the carbon-carbon double bond cannot rotate. So if you remember with alkanes, it didn't really matter, as long as you had a continuous chain, it didn't really matter how they're drawn because there's rotation going on. But that double bond can't rotate, it's rigid. So the groups that are connected to those carbons in the double bond are stuck in their positions. So if the groups that you're looking at across the double bond, so you have your C double bond C, and let's say for instance, where I'm just going to do, okay, HH, and I'm going to put R. We use R to represent basically any type of organic chain. And so if they're on the same side, so notice they're on the same side of each other, they're both on top, we call this cis. If you handwrite it, you write cis and you underline it. In text, it's italicized. If they are on opposite sides of each other, so we have our double bonded carbons. Okay, so they're on opposite sides of each other. This is called trans. So here's a couple examples showing some structural and geometric isomers of butene. So 1-butene can't have cis-trans. And it looks like when you're looking at the structure, it looks like, oh, there's got to be something here. But one rule with cis-trans is if you have the same things coming off of one of your double bonded carbons, then there is no cis-trans. It doesn't matter because this group here, we could say, oh, look, it's on the opposite side of this hydrogen, but it's on the same side as this hydrogen, so it's the same. It doesn't matter. Okay, so it cancels out. So 1-butene doesn't have the cis-trans isomerization, but 2-butene does. So if we look at cis-2-butene, we see that these groups, these CH3 groups coming off of the carbon-carbon double bond are on the same side of each other. So this is the cis-2-butene. Whereas this other one, they're on opposite sides. So this is trans-2-butene. So let's talk about some reactions and we'll look at some examples. The carbon-carbon double bond is a very reactive functional group. It's more reactive than alkanes, and that's because the pi bond is really easy to disturb. One type of reaction that they undergo is called an addition reaction. And so what you're doing is you're adding something across the double bond. So you're breaking the double bond of carbons and you're adding something to them. So we change the hybridization of those carbons then from sp2 to sp3. So we're going from a double bond to a single bond. So this is an example of an addition reaction. We're taking ethene and we're giving it Cl2. So each of these chlorines is going to attach itself to each of the carbons across that double bond, breaking the double bond, changing it to a single bond, and now each one has added a chlorine. Nothing happened to the hydrogens, nothing aside from the hybridization changed on the carbons. We just added chlorines to them. So here is an example. We want to provide the IUPAC names for the reactant and the product of the halogenation reaction shown here. Halogenation addition, so we're saying halogenation because it's a halogen. So let's first name our organic reactant here. First step, longest carbon chain. You see 1, 2, 3, 4, 5. We don't have any branches coming off, so we know this is a pent. We have a double bond, so it's an ene. So we know that. So now carbon numbers, we want the lowest number. So that means that this end carbon needs to be number 1. So that means this is 2, 3, 4, and 5. So carbon 2 is where our double bond is. So this is 2-pentene. But we also have to worry about cis-trans. So notice we can let's kind of scribble all these hydrogens and redraw them like this. So notice when we look across the double bond, we see the two groups coming off of the carbons in the double bond are on the same side. So that means they are cis. So this full name is cis-2-pentene. So now for our product, we're taking these two chlorines and we're going to add them to each carbon in the double bond. So we're going to break that double bond. So now single bonds. And this carbon already had a CH3 and a hydrogen. So one thing you can always do when you know that, okay, this is an addition reaction, you go, okay, I'm going to just draw what I know isn't going away. And then I go, okay, and then each one gets a chlorine. You can also, you don't have to try to fix the zigzags. You could also literally draw this, go, okay, I have CH3, CC, or go CH, CH, CH2, CH3, and then go, okay, Cl, Cl. Remember, they rotate. It's the same thing. These are alkanes now. Single bonds can rotate, so it doesn't have to be perfect. All means the same thing. Okay, here's another example. We want to figure out the IUPAC names for the reactant and the product of this halogenation reaction. So let's start by naming this reactant. We see 1, 2, 3, 4, 5, 6 carbons. Oh, whoops. Oh, let me go back. We forgot to name our product. So we know our product has, from our first example, still has 5 carbons. So this is a pent. This time now it's an ane, right? Because now it's an alkane. We don't have cis-trans since it is an alkane now. And we added a chlorine to each carbon in the double bond. So now we have 2 chlorines, meaning we have a dichloro. And they went on the double bonded carbons in carbon 2 and carbon 3. So we have 2,3-dichloropentane. Okay, back to this other example. We have 6 carbons, which means we have a hex and double bond in there, so it's a hexene. So numbering our carbons, let's say this is 1, 2, 3, 4, 5, 6. So carbon 3 has our double bond, so we have a 3-hexene. Now notice with the way it's drawn, these 2 hydrogen are on the same side as each other, so that means we have a cis 3-hexene. So that's our name there, and now we need to go ahead and get our product. So we know we have 6 carbons. And we also know that nothing's happening to their hydrogens. I'm just going to write them in. And we know that the chlorine is going to add to each carbon across the double bond, which those are carbons 3 and 4. So that means carbon 3 and carbon 4 get a chlorine. And its name, it's a hexane, since now we have all single bonds. No cis-trans, since we're all single bonds. And we have 2 chlorines, so now we have a dichloro. And since we know the positioning already of the carbons that took each chlorine, we know they're at 2, 3. So now we have 2,3-dichlorohexane. Now, another type of hydrocarbon we have are the alkynes. It takes all kinds to make the world. Yeah, I know it's corny, but chemists, especially organic chemists, have lots of puns and jokes. So these are hydrocarbons with one or more triple bonds. These are also considered unsaturated hydrocarbons since you don't have the maximum number of hydrogens for each carbon. And the carbons in the triple bond are joined by one sigma bond and two pi bonds. And they're sp hybridized, so just sp hybridization, and with a bond angle of 180 degrees, so these are linear. They're very similar naming scheme to alkenes, but instead of "ene," they end in "ine." So you do have to number what carbon has the triple bond once you start at 4 carbons. So alkenes are more reactive than alkanes, and alkynes are more reactive than alkenes. For instance, acetylene. So acetylene torches. Those get really, really hot, right? They're used for cutting metal. Alkynes can also, or alkynes, excuse me, can also undergo addition reactions, kind of like the alkenes, but you use twice as much reagent because you're adding twice across the double bond. So here's ethine, aka acetylene. You don't have to know the name acetylene, but if I gave you the structure and I asked you to name it, you would name it as ethine. So 2 carbons, eth, and then yne, ine, to tell me they're triple bonded. Again, you don't have to number the carbon number because no matter what, it's carbon 1 where the triple bond is. And then here's an example of the addition reaction. So we have each bromine starting off going to a carbon, so then that tells us, okay, now we go down to a double bond. And then we have 2 more bromine that are each going to go to a carbon, so then that gives us 1,1,2,2 tetrabromoethane. So ethane, longest carbon chain, and then doesn't matter, we'll say, okay, this one's 1, this one's 2. So carbon 1 has 2 bromine, carbon 2 has 2 bromine, so we have total of 4, so we have tetrabromo. And then we have to specify it goes 1, 1, 2, 2. So someone looking at our structure, our name doesn't think it's 1, 1, 1, 2 tetrabromine. 1, 1, 2, 2 tetrabromoethane. One thing I love about the IUPAC naming is it's very straight up on what you're looking at. So here is an example. We're told to describe the geometry and hybridization of the carbon atoms in this molecule. So carbon atoms 1 and 4, each of these carbons have 4 single bonds. So these are good old sp3. Now carbons 2 and 3, though, have the triple bond and single bond, so they're going to be linear sp. Now let's go ahead and name this structure. I know it doesn't show it here, but I want to name it. So we have 4 carbons, so we have a bute, and we have a triple bond. So this is butyne. I know that looks weird. And now we do need to specify where the triple bond is, because we could have the triple bond on carbon 1 if we wanted, but in this case, it's on carbon 2. So this is 2-butyne. So here's another example to look at. We want to identify geometry and hybridization. So carbon 1, it has a triple bond and a single bond, so this has to be sp. Same goes for carbon 2. Carbon 3 now, notice it has a double bond and a single bond, so this is sp2. Same with carbon 4, and carbon 5 is our good old sp3 friend. So I'm tempted, and I think I will, and this will be a reward for those of you that watch the lectures. I may put this exact molecule on your exam as an extra credit question to name it. And it's kind of a mean question because of the way because we have a double bond and a triple bond. So the way we would do this, we have a pent, dash. So this is weird. You sometimes have to put it in the middle of the name. Pent dash 3 een dash 1 dash ein. I'm going to look it up to make sure I'm right there. Pent dash 3 een dash 1 ein. Yep, that is a real name. Not worrying about cis trans there, because it's actually a little different, but there we go. Or the other way you can name this is you would say 3-pentene -1 ein. I will also accept that name. There's some other parts to this name, but we're not worrying about that part. So there we go. So there's some extra credit for you guys. So now we have a new group called aromatic hydrocarbons. And these are compounds containing ring structures, and they have bonding that must be described using the resonance hybrid concept of valence bond theory or the delocalization concept of molecular orbital theory. So these are special ring structures. These aren't like that one we saw earlier that was just all single bonds. No, these are special rings. So benzene, which has the formula C6H6, is the simplest aromatic hydrocarbon. And these more so undergo substitution reactions where you change out a hydrogen on the ring, more so than addition, because in a ring, in the aromatic hydrocarbon, so benzene looks like this. You have alternating double bonds. It does have resonance structure, so also might be drawn like that. Okay, so what's happening is these double bond, these pi orbitals, the electrons are actually delocalized, so meaning that they're being shared. All the electrons from all 6 carbons are being shared above and below the benzene ring. So it doesn't like to break those carbon-carbon double bonds. So instead, each of these there's a hydrogen coming off of each carbon here to finish its 4 bonds. So benzene would much rather give up one of those hydrogen that's not in the ring and put something else coming off of it than break those carbon bonds in the ring. So each of the carbons in the benzene ring is sp2 hybridized. And those p orbitals, like I was kind of talking about, are perpendicular to the plane. And each of the 6 bonds in the ring and the carbon bonds are equivalent. So they're actually not technically double bonds. They're more like they're in between a single and double bond. They're like a carbon-carbon 1.5 bond. And because of that, in resonance, you may see benzene drawn like this, with a circle in the center to show aromaticity, or that those double bonds are all being shared. There's a bunch of benzene derivatives where, again, we take off the hydrogens and replace them with different substituents. So this is just showing that resonance, and then benzene drawn with that circle in the center as the condensed formula. Here's some examples of some substitutions on a benzene ring. Toluene is something you may have heard of. You may have heard of the compound trinitrotoluene, which is TNT. So there's a little trivia fact for you. So a toluene is when you have a benzene ring with a methyl group coming off. Xylene has 2 methyl groups coming off, and styrene, which is the monomer that you use to make polystyrene. These are just some examples. There's a ton of other examples. So here's an example. One possible isomer created by a substitution reaction that replaces a hydrogen atom attached to the aromatic ring of toluene with a chlorine atom is shown here. Draw 2 other possible isomers in which the chlorine atom replaces a different hydrogen atom attached to the aromatic ring. So we're already given one isomer, and we want two other possibilities. So we're starting with toluene. Okay, and notice it doesn't really matter where the CH3 is because we can just spin it around and it'll be in the same place. So I'm just gonna put it here just to kind of match what they did. And they've already drawn the chlorine here, so we need to put it in some other places. So because they drew it there, we technically can't say it's here because that's actually the same molecule. If we were to just rotate this around, we'd get the same thing. Okay, so we could put one here. So there's one possibility. There's actually specific names, fun fact, for these positions. And then the other place would have to be straight across from the CH3. So there's our two other isomers. So our other example, draw 3 isomers of a 6-membered aromatic ring compound substituted with 2 bromines, and these are the answers right here. I forgot to delete this. But nonetheless, these are the 3 isomers with 2 bromines. You know, this guy here on the end, God, I'm so bad at drawing benzene rings. Like, I'm not good at drawing them when they're flat on top. I like to draw them where you have a point on top. I know that's weird, but so if we drew the bromines like this is the same molecule. I just want to make sure you guys understand that those are the exact same things. If we were to rotate this guy over, we'd get the same thing.